Hi students, in this video I would like to discuss about operations on binomial heaps. In the previous video we already discussed about the properties and definition of binomial heap. So first one is creating a new binomial heap. So to make an empty binomial heap, the make binomial heap procedure simply allocates and return an object h where head of h equal to nil. We already studied about head of h. It is the pointer which points to first node in the root list. Here, with the help of the procedure make binomial heap, we are actually creating an empty binomial heap. We already studied for an empty binomial heap, head of h will be nil. So since it takes only constant time, the running time will be theta of 1. Next procedure is finding the minimum key. In the previous videos we studied the minimum element will be always in the root list, because binomial heap is a collection of binomial trees where each binomial tree follows min heap property. So one of the roots will contain minimum key. The procedure binomial heap minimum returns a pointer to the node with minimum key in an n node binomial heap H. Since binomial heap is min heap ordered, the minimum key must reside in a root node. The procedure finds the minimum element from the root list. The implementation assumes that there are no keys with value infinite. So here, with the help of this binomial heap minimum, we are just traversing, or we are just finding the minimum element from the root list. The running time of binomial heap minimum is O of log n, since there are at most floor of log n plus 1 roots to check. Because here we are only searching in the root list, and the maximum number of root lists possible is floor of log n plus 1. So the complexity for this procedure will be O of log n. We just look at this procedure. Here y is a pointer which will be initialized as nil. X contain head of h. Minimum is a variable which is stored with infinite. While x not equal to nil, that means initially the x will pointing to the node 10. Anyway, x is not nil. If key of x less than minimum. Minimum is infinite. Here key of x is 10. 10 is less than infinite. So I am going to store 10 in minimum and x in y. Y is actually initialized as nil. Address of x, that means address of node 10 will be stored in y. Next what happens, x equal to sibling of x. Now x points to 10. What is sibling of x? Sibling of x is 1. In the root list, sibling of x contain address of next node in the root list. So now x points to 1. Again x is not equal to nil. Actually our key of x is 1. Min is already 10. 1 is less than 10. So these two statements will be executed. Min will become 1. Y becomes address of 1. Y becomes address of 1. Next again x equal to sibling of x. So it is moving to the next node. So key of x is 6. 6 less than 1 is false. So these two will not be executed. This step will be executed, that is step 8 will be executed. What is sibling of x? There is no sibling to this node 6, so that will be nil. So x becomes nil. Now x not equal to nil is false. So this while loop will not execute anymore. The y value will be returned. Y value is actually address of 1. I hope you understood this binomial heap minimum. In this example, this procedure will return address of node containing 1. So next is a auxiliary procedure which will be used in the further procedures, that is binomial link procedure. The procedure binomial link y, z links the bk minus 1 tree rooted at node y to bk minus 1 tree rooted at z. So here binomial link I am passing two parameters y and z. Y is the root node of a bk minus 1 tree. Similarly, z is also a root of bk minus 1 tree. So we already studied when two bk minus 1 trees are combined, we will get a bk tree. It makes z the parent of node y. When I am applying binomial link on two bk minus 1 trees with root y and z, in the resultant bk tree, z will be the parent node of y. Node z thus becomes the root of a bk tree. Suppose I have two bk minus 1 trees with m and n as roots. I am calling m comma n. So this y value will get m and z value will get n. P of y equal to z. That means parent of m will be n. Parent of this node contain a parent field. There I am storing address of n or n. Then sibling of y equal to child of x. Sibling of y equal to child of z. That is sibling of m equal to child of n. What will be the value of child of n? Child of n contain address of leftmost child. Child of n contains address of leftmost child. When these two trees are linked, that leftmost child become sibling of this m. Leftmost child of n becomes sibling of m. That's why sibling of y equal to child of z. Then child of z equal to y. So here in this node we have a child field. It actually contains address of leftmost child. When this binomial tree with root m is linked with n, this m becomes leftmost child. That's why child of n will be stored with m. One more thing will happen. One more child is added to n. So the degree of n will be incremented. So degree of z equal to degree of z plus 1. So always remember, when I am calling binomial link of y comma z, z becomes the parent. That means the second parameter becomes the parent. One more example is there. Binomial n comma m. In that case, m is the second parameter. M becomes the root node of the bk tree. Next procedure is uniting two binomial heaps. So here we have two binomial heaps. We want to combine those binomial heaps. So given two binomial heaps h1 and h2, binomial heap union h1 comma h2 creates a single binomial heap. First we simply merge two binomial heaps in increasing order of degrees. After that we need to make sure that there is at most one binomial tree of any degree, so that we combine binomial trees of same degree. So here we are going to combine two binomial trees h1 and h2. So we already know in binomial heap, binomial trees are arranged in increasing order of degrees. So here we are combining two binomial heaps. So these two binomial heap may contain binomial trees with same degree. One more property we have studied. In a binomial heap we have only one binomial tree with a degree k. No two binomial trees have the same degree. So that's the meaning of this point. After that we need to make sure that at most one binomial tree of any degree, so that we combine binomial trees of same degree. So here the first step is we simply merge two binomial heaps in increasing order of degrees. That this point we will discuss in the later slide. When we combine two binomial heaps, we may get two binomial trees with same degree. With the help of this procedure, we are going to maintain that property. Maintain that property means in a binomial heap we can have only one binomial tree with a particular degree. So for that we have to traverse the list. Traverse the list means traverse the root list. While traverse the list of merged roots, we keep three pointers: priv x, x and next x. So while traversing we may come across four cases. Let's see the first case. Degree of x equal to degree of next x. So here we have three pointers for the traversal. This is x. The previous node will be priv x. Next node will be next x. So sibling of next x means the node right to next x. In first case, degree of x not equal to degree of next x. Here degree is k. Here degree is l. So the first case is satisfied here. So what we have to do, simply march ahead the list. So the pointers will be shifted towards the right. The C becomes x, D becomes next x, and B becomes priv x. So we just simply march ahead. That means the pointers will be shifted to the right hand side. Next case is degree of x equal to degree of next x equal to degree of sibling of next x. That means three binomial trees may get same degree. So we already discussed, we combine two binomial heaps h1 and h2. When we combine two binomial heaps, we will never get three nodes with same degree. Why? Because h1 will contain a binomial tree with degree k. h2 may contain binomial tree with degree k. So when we combine it, we will get two binomial trees with same degree. While combining, this condition will not occur. Case 2 actually occurs after execution of case 3 or case 4. So we have to study two more cases. This case 2, that means this degree of x equal to degree of next x equal to degree of sibling of next x may occur when we execute case 3 or case 4. So there also what we have to do, simply march ahead. That pointers will be shifted towards the right. After that, what will happen? In next iteration, either we execute case 3 or case 4. So case 2 will be always followed by case 3 or case 4. Next is case 3 or case 4. So one of the condition for case 3 and case 4 is degree of x equal to degree of next x not equal to degree of sibling of next x. So for both case 3 and 4, this condition must be satisfied. For case 3, key of x less than or equal to key of next x has to be satisfied. Else condition, key of x greater than key of next x will be satisfied for case 4. So this condition is common for case 3 and case 4, and this based on the key value of x and key value of next x, case 3 and 4 will change. So first we look at the case 3. Case 3, degree of x equal to degree of next x. Here we have two bk trees. That means these two trees have the same degree. What we do there is, if key of x is less than key of next x, that means this b is less than or equal to c. What we have to do? We have to link these trees. We already studied binomial link procedure, but to satisfy binomial heap property, since b is less, when we combine these two trees, b must be the root of the tree. So what we do is binomial link next x comma x will be called. If you remember that link procedure, the second parameter will become the root node. So here we combine these two bk trees to form a bk plus 1 tree with b as the root, since the value of b is less than c, to maintain the heap property. Similarly, in the case 4, we are comparing key of x and key of next x. So here key of x is greater, that means key of next x is less than. So here also we are linking these two binomial trees. To maintain the heap property, we have to make c as the root. For that, what will we do? We will call binomial link x comma next x. So in case 3, this next x will be removed from the root list and linked to x, and this binomial tree will be linked with x. So this left hand side we have already discussed. This is the pseudo code for binomial heap union. First step, h equal to make binomial heap. We already studied this procedure to create an empty binomial heap. That means head of h will be stored with nil. Next I am calling a procedure called binomial heap merge h1 comma h2. This procedure simply merge two binomial heaps in increasing order of degrees. So this binomial heap merge is very similar to the merge procedure in merge sort. That's why that pseudocode is not discussed here. This procedure is almost similar to merge procedure in merge sort. Here we are merging these two root lists in the increasing order of degrees. Next, free the objects h1 and h2, but not the list that point to. We had 2 pointers h1 and h2. It is clear. It is just for garbage collection. If head of h equal to nil, then return h. So this condition occurs only when we are merging two empty lists. You just imagine h1 is nil, h2 is nil. And when we apply binomial heap merge, this h also becomes nil. In that case, just return h. H will be nil. This is to counter that condition where both h1 and h2 will be nil. Next is proof of x equal to nil. Essentially, previous of x will be stored as nil. X will be initialized with head of h. Next of x will be sibling of x. Next of x means node next to x in the root list. It will be sibling of x. So this is the while condition. You just look in the if condition in the line number 10. Degree of x not equal to degree of next x. That is actually the condition for case 1. Degree of x not equal to degree of next x. Or sibling of next x not equal to nil. It is sibling of next x become nil once we reaches the last node in the root list. So it is only to counter that condition. You just look at this condition. Degree of sibling of next x equal to degree of x. This is actually the part of case 2. Degree of next x equal to degree of sibling of next x. Again you look at this condition. This entire if condition will become true when either this condition is true or this condition is true. There are two conditions are there. This entire if condition will be true if either of these two conditions will be true. You just imagine this first condition is false. First condition is false means degree of x is actually degree of next x. So you already studied the OR condition. If the first condition is false, you just remember about the OR condition. The second condition is checked only when first condition is false. So when we are checking the second condition, what is the actual value? Degree of x will be equal to degree of next x. Then only we are going to test the next condition or the second condition. So what's the meaning of the second condition? Degree of x will be equal to degree of next x, and also it is equal to degree of sibling of next x. So I think this case 2 condition in the left hand side and the case 2 condition in the right hand side is clear now. So in both the cases what happens? We have to march ahead. That means now x becomes previous of x and next x becomes x. And here line number 21 to set next x equal to sibling of x. You just look at line number 11, 12 and 21. While executing this 11, 12 and 21, the pointer will be shifting towards the right. Again you just look at the if condition. If condition means when both these two conditions are false, we will check for the if condition. If condition, if key less than or equal to key of next x. That means this if condition is checking whether it is case 3. If it is false, the meaning is key of x is greater than key of next x. Then we will execute line number 16, 17 and 18. The 16, 17 is to maintain the head pointer. So when key of x less than key of next x, binomial link next x comma x will be executed. In the other case, that means key of x is greater than key of next x, this binomial link x comma next x will be executed. So this will be more clear when we study the example. Next we look at the example. Here I have two binomial heaps, h1 and h2. First, what will we do? We will merge these two lists in the increasing order of degree. So this is the output of binomial heap merge of h1 and h2. So it is arranged in increasing order of degree. 12 has degree 0, 18 has degree 0, 7 having degree 1, 3 is having degree 1, 15 is having degree 2, and the 6 is having degree 4. So now after executing binomial heap merge, we will get a merged list. H1 and H2 is cleared because there is no need of H1 and H2 later in our program. Anyway, in this example, head of H is not nil, so H will not be returned. Initially, proof of X will be nil. Head will be stored to X. That means X is pointing to 12, and also head of H is also pointing to 12. Next X pointer will be stored with sibling of X. So next X will be pointing to this node 18. So next X is not equal to nil. So these steps are going to execute. You just test the condition. Degree of X not equal to degree of next X. This condition is false. This condition is false. Sibling of next X is not equal to nil because sibling of next X is 7, so it is not equal to nil. Degree of sibling of next X and degree of X. What is degree of X? 0. What is sibling of next X? 7. What is its degree? 1. 0 equal to 1 is false. That means these two conditions are false. So it is not case 1 or case 2. So it will execute this condition if key of X less than key of next X. What is key of X? Key of X is 12, key of next X is 18. So that condition is satisfied. Sibling of X equal to sibling of next X. So I am going to link this 12 and 18, and I want to make 12 as the root of that binomial heap. So in the field sibling of X, I want to store sibling of next X. Sibling of next X is 7. So you just look at this diagram. I want to link 12 and 18, and 12 becomes the root. After that, who will be the sibling of X? Sibling of X will be 7. Who is 7? Sibling of next X. So sibling of X equal to sibling of next X. So this pointer is created first. 12 is linked with 7. Next, binomial heap of next X comma X. So this 18 and 12 will be linked. So this is an example for case 3. So now the binomial heap look like this. First 3 nodes having same degree. I already told you case 2 may occur after the execution of case 3 and 4. Just look at the second case. Here it is case 2. What we have to do? We have to just march ahead. Now X is pointing to 12. Here X will be pointing to 7. Next X will be pointing 3. Actually, initially proof X is nil. Now proof X is pointing to 12. You just look at this condition. Degree of X not equal to degree of next X. For these two binomial trees, binomial heaps, the degree are same. So this condition is false. Sibling of next X not equal to nil. Sibling of next X is 15. So it is not equal to nil. Degree of sibling of next X equal to degree of X. Who is sibling of next X? 15. Degree of 15 is 2. Degree of 15 is not equal to degree of X. So this condition is also false. So it is not case 1 or case 2. So here key of X less than or equal to key of next X. 7 is not less than 3. So it is actually case 4. Here one more condition is to check to maintain the head. Proof of X equal to nil. Proof of X is not equal to nil. So else. So case 4 is going to execute. So I am going to link this binomial heap and this binomial heap. I'm going to link binomial heap X and binomial heap next X. After linking, this 3 will become the root of that binomial heap. So I have to create a link from 12 to 3. 12 to 3. For that I am using this term, this statement, sibling of proof X. Sibling of proof X is now actually 7. So I am linking with 3. I am storing with X. So this link is created between 12 to 3. Then binomial heap link X comma next X. I want to make 3 as the root. So I am calling X comma next X. Next what happens, one more statement is there, x equal to next x. So here actually 7 is removed from the root list. So 7 is removed from the root list. Actually x was pointing 7. So when 7 is removed from the root list, x will be pointing to 3. Now x is pointing to 3, and next x equal to sibling of x. So 15 will becomes next x. Again next x not equal to nil. So again this condition will be checked. So here if we notice it again, case 3 will be satisfied. That means because these two binomial trees having the same degree, this x and next x will having the same degree. Here also x and next x is having the same degree. So here 3 has the lesser value. So case 3 will be executed. That means this binomial tree will be linked with 3. So we'll get a bigger binomial tree. Here in this diagram, case 1 is satisfied. So we just march ahead. So now we get a binomial heap with binomial trees of different degree. At some point this condition will become false, because when we traverse ahead or when we march ahead, at some point next x becomes nil. At that time this algorithm will terminate. Next is analysis of binomial heap union. Just imagine h1 contains n1 nodes and h2 contains n2 nodes, so that n equal to n1 plus n2. Then h1 contains at most floor of log n1 plus 1 roots, and h2 contains at most floor of log n2 plus 1 roots. So h contains at most floor of log n1 plus floor of log n2 plus 2. We are just adding these two. This will be the total number of elements in the root list. Anyway, it must be very less than 2 of floor log n plus 2. In another way I can say floor of a plus floor of b is very less than or equal to floor of a plus b. The same logic is used here. So this we are merging two binomial heaps which contain n1 nodes and n2. This binomial heap merge will not take more than log n time. It is never going to take log n time. So the time to perform binomial heap merge is thus O of log n. So here we have while loop. Each iteration of while loop takes O of 1 time. This always takes a constant time. This always take a constant time. At maximum this while loop will execute for log n times. So the entire procedure will take only log n time. Next procedure is inserting a node in binomial heap. The following procedure inserts node x into binomial heap h, assuming that x has already been allocated and key of x has been filled in. So this procedure works with an assumption. It will insert a node x. For that node x, the key value will be already stored and that node block is already allocated. So actually I am going to insert that node into a already existing binomial heap. It's already existing binomial heap h. So here h dash equal to make binomial heap. So h dash will be an empty binomial heap. We already have a node x. Parent of x will be stored as nil. Child of x will be stored as nil. Sibling of x will be stored as nil. Degree of x will be 0 because that x didn't have any children. It only have a key value. Head of h dash equal to x. So when I created h dash, the value of h dash, head of h dash is actually nil. After execution of statement 1, h dash will have the value nil. Now h dash is stored with x. So actually binomial heap h dash now contains one element. Binomial heap h dash now contain one element. We already have a binomial heap h. So now we have two binomial heap. One is binomial heap h and another one is binomial heap h dash with only one node. So in short we have two binomial heaps now, h and h dash. Here in the line number 7 you just apply binomial heap union of h and h dash. So once again I am saying I already have a node x will contain key value. Now I have only one node. That node is converted to a binomial heap by these statements. The name of that binomial heap or the reference to that binomial heap is h dash, and we have an already existing binomial heap h. So with the help of the procedure binomial heap union, where we are passing h and h dash, we are inserting x into the binomial heap h. The procedure simply makes a one node binomial heap h dash in O of 1 time. So for executing line number 1 to 6 we will take only constant time and unite it with n node binomial heap in log n time. We already studied binomial heap union will take O of log n time. So the complexity of binomial heap insert is also O of log n. Okay, next procedure is extracting the node with minimum key. So actually what this procedure do is it will remove the node with minimum value from the binomial heap. We already know the minimum value will be in the root list. The following procedure extracts the node with minimum key from binomial heap H and returns a pointer to the extracted node. I'll try to explain this pseudocode with the help of an example. Find the root x with minimum key in the root list of H and remove x from the root list of H. We already studied how to find the minimum from the root list. So in this example, this 1 will be the node with minimum value. So first find 1 and remove it from the root list. So I will get a structure like this. That 1 is removed from the root list. Now the root list contain only 37 and 10. H dash equal to make binomial heap. So this make binomial heap will create a empty binomial heap. Reverse the order of list of x children. X is 1. X has some children. You just reverse the order of x children. Just reverse the order of the linked list of x children. So I will get a structure like this. This is actually a binomial heap. This is actually a binomial heap. And set head of h dash to point the head of the resulting list. Already created an empty binomial heap with h dash and the head of the resulting list is stored to head of h dash. Now I am having two binomial heap, head of h and head of h dash. So I just apply binomial heap union on h and h dash. So I will take union of head of h and head of h dash. I will get a new binomial heap. You just compare this a and d. Both are binomial heaps, but that minimum key one is removed. So it's a simple procedure. So the time taken for binomial heap extract min is also log n. So that's all about binomial heaps. Thank you.